Today we are going to take on a topic of optimizing efficiency and productivity from the modern blast furnace. As you must be knowing, the blast furnace oxygen steelmaking route is a backbone of global steelmaking, which contribute around more than 70%. And with this, we can say that a lot of iron is getting produced from BF route, but at the same time, we do also know that it emits a lot of CO2 emission in the atmosphere, and that also is a very burning agenda. That's and it's also massive. So our mission is clear: optimizing operation, which will bring down this CO2 emission to a lower level. We have to improve the resource efficiency as well, and and at the same time we also need to adopt the state of art technologies to make the blast furnace both productive and sustainable. So we can say that we need to increase the process efficiency, the material efficiency, and the use of technology. So as you can see that so we can say that at the heart of efficiency there are two pillars, the reductant and the ferrous material. As for the resource efficiency improvement in the blast furnace is concerned, as we know that coke along with the coal is not just fuel, it provide heat, generates CO for reduction, support permeability, and even filters impurity. So the best operation now aim for less than 300 kilo of coke per ton of hot metal with injectant replacing the rest. So on the other hand, the ferrous material like sinter, pellet and lumps must be both chemically and physically strong to ensure smooth gas flow and consistent hot metal quality. So key lies in balancing these inputs strategically and very minutely so that we have a cost efficiency, process stability, and environmental gain. So we need to introspect the three factors very in a delicate way and need to see that where we have got a maximum benefit. Now coming to the operation control, of course operation control are three, and this is the first control, which is about the burden quality and the permeability. So as you know, the gas flow inside the furnace depend heavily on the permeability, and ore layers with a smaller particle and fines block the gas movement compared to coke, as its size is lesser than the coke. So fines below 5 millimeter rising from poor screening or reduction disintegration are the biggest culprit, as all iron makers knows. So they choke the void spaces, increases the resistance and cause localized blockages. And once localized blockages started occurring, there is a unsymmetrical reduction occur, and which leads to further fluctuation in the quality and the fuel rate. So that's why screening of 5 to 6 millimeter using stable material, minimizing pallet swelling, and even redistribution of fines are very essential. Remember, permeability is the lifeline of furnace efficiency, and wherever in all operation, these need to be focus point for all process experts. Now coming to the operational control number two, which is focus, which is concentrate around burden distribution and gas flow. So gas flow always takes a path of least resistance, as we all know. That's why burden distribution is the operator's primary tool to control gas flow. The ideal approach then is to maintain an ore-free center, ensure nearly horizontal layers, and use nut coke along the wall. So these are the basically three secrets. If operator follow, then we have got a maximum outcome. So these measures stabilizes the blast pressure, improve permeability, and reduce wall heat losses. But poor distribution can lead to W-shaped cohesive zones and high wall heat losses once W-shaped cohesive zone occurs and overall efficiency drops. And simply we can say that a small distribution equals a smart productivity. Now, coming to our operational control number three, which is about a injectant management and thermal control, and it's supposed to be the very important. So, injectant like pulverized coal and natural gas are game changer. They reduce very expensive coke use, lower CO2 emission, and can replace up to 40% of coke requirement. The thermal heartbeat of the furnace is the raceway adiabatic flame temperature or RAFT, and oxygen enrichment boosts RAFT and productivity, while natural gas rich in hydrogen keep RAFT lower but ensure efficient reduction at high temperature. And real-time monitoring and adjusting injectant rates are the basically key to avoiding thermal upset and keeping the furnace in the very balanced shape. So injectant knowledge and heat sink due to its injection and the reduction potential is in totality to be evaluated by operator, and best trade-off is to be look into get a maximum result, and this will optimize our processes very efficiently. Now coming to the our operators also coming to the operational challenges, addressing operational challenges. So in this we can say that our operators also face challenges and access fines, moisture, slow reduction, alkali, zinc recirculation, damage refractory, irregular body and descent, leads to hanging, sleeping, unsymmetric situation, uneven temperature on the top, and all these disruption, which is not symmetric, not regular, not similar sort of a profile when furnace is running good. So each of these disruption gas flow disrupt the gas flow and stability of the furnace in a big way. So what is the solution? The solution is the strong furnace design, consistent distribution, and proactive thermal management. And tackling these head on keeps the furnace both productive and reliable. Now, coming to the operator's toolkit and continuous improvement. So modern furnaces comes equipped with power toolkit like rear cameras, top cameras, SOMA system, pressure taps, and in-body probes. So these tools gives real-time insight into a raceway, gas flow, and temperature profiles. Expert system analyze this ocean of data, helping operators diagnose problems and even take corrective action automatically. But technologically alone is not sufficient. We need to see the data in complementary to each other. The real edge comes from understanding the know why. Only then can operator go beyond the best practices and drive continuous improvement. Even though data is sourcing from a different probing equipments, but we need to see independent to other probing equipment data, and then we can have got a much better understanding. Now coming to the conclusion, which is towards sustainable and high performance of the furnace. So we can wrap up and achieving peak performance in the blast furnace. We can say that it demand integrated optimization, and from raw material quality to burden distribution, injectant management to thermal control, it's all interconnected. So stability is the foundation, and with a stable burden descent and smooth gas flow, we can cut fuel rates, maximum efficiency, and extend campaign life. So the future lies in continuous innovation and reducing the carbon footprint. The operator's responsibility then is what? Is their responsibility is to lower carbon rates wherever possible, adopt higher PCI, and work towards greener steelmaking.